Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is an easiest thing to prove, but could also check that if polynomial is quadratic, then it must be a sum of squares. This is basically, if you think of quadratic forms, you can do it by diagonalization of symmetric matrices. Okay, and then, well, you could say, well, how far can we extend this? And in the 1890s, Hilbert proved the theorem that said that basically these are essentially the only cases when a non-negative polynomial has to be a sum of squares. So let's go to Hilbert's theorem. So, well, let P of x be a non-negative polynomial. So when does a non-negative polynomial have to be a sum of squares? Well, if it's polynomial in one variable, if it's a quadratic polynomial. There is one more case that's sort of an outlier where you don't have enough freedom. It's a polynomial in two variables of degree 4. And in all other cases, there actually exist non-negative polynomials that are not sums of squares. Okay, so however, it happens that Hilbert did not give a particular example. He proved the existence of such polynomials using some classical algebraic geometry, but he did not show one polynomial like this. But he did, however, later show that every non-negative polynomial in two variables has to be a sum of squares of rational functions. So, so you write a polynomial as a sum of squares of a rational function, and if you reduce it to a common denominator, then everything is, well, cancels. You get the polynomial back. And then this became Hilbert's 17th problem, which was, can a non-negative polynomial always be written as a sum of squares of rational functions? And this is actually true. So Artin and Schreier have solved Hilbert's 17th problem, and their solution has started a lot of research in real algebraic geometry. But if you would actually like to get your hands on such representation, then it's entirely unclear how to get it. So for example, you might have to use rational functions of very large degree, denominators of very large degree, in order to get your polynomial. So the way that I think about it is, so if you could write your non-negative polynomial as a sum of squares of polynomials, then you're writing it as a sum of squares of objects that are actually even simpler than your polynomial. They're of polynomials of degree k. While if you're writing it as a sum of squares of rational functions, then you're writing it as a sum of squares of objects that are significantly more complicated than your polynomial. Okay, so this is a great theorem, and it gives you a certificate, I guess, for non-negativity that you could check the sum of squares representation. But if you wanted to get your hands on this representation, then it's entirely unclear as to how to do it. Yeah? Twice so, the meaning that the degree is even, otherwise you can't have a non-negative polynomial. No, it doesn't have to be homogeneous. Like x squared plus twice x plus 1, is also x plus 1 squared. No, like the high, if your leading degree term has odd degree, then you can't have non-negativity. Right, exactly. Later we'll just talk about homogeneous polynomials, but for now, yeah, you need to have the highest degree term has to be of even degree, otherwise you can't have non-negativity. Okay, any more questions? No? Okay. So, all right, so now let's go to explicit examples. So as I said, Hilbert just proved the existence of such polynomials, and it took about 60 years since he proved it to actually for somebody to come up with one, because, well, it's not clear how one should do it. So, you have to construct a polynomial that is non-negative, but not in an obvious way. And by that I mean not a sum. If you could write it as a sum of squares, then it would be obviously non-negative, but not something that you would want. Okay, so the first such polynomial was constructed by Motzkin, and I think what helped is that he was not aware that this was actually a hard problem. So he constructed it, and he just did it as an example of a curious thing that happens. And then he was informed that this is actually more interesting than he himself thought. Okay, so I wrote it out hopefully correctly. Okay, so here it is. It's pretty simple polynomial. So, but the main thing is, so why is it non-negative? There is a good reason it's non-negative because of the arithmetic mean geometric mean inequality, right? And then you need to do some basically term-by-term analysis. You need to say, well, let me write M as a sum of squares. What terms can occur? And then in the end, you arrive at a contradiction. Okay? And yeah, so this is pretty much the simplest example of this phenomenon, but it doesn't really, I mean, well, you could look at it, but I'm not sure it tells you very much as to what exactly is happening. Okay. So more an explicit example. So later people have been able to construct more of these polynomials explicitly, so non-negative polynomials that are not sums of squares, but there aren't so many families of examples. You could sort of count them on probably both of your hands. So it's not, well, I guess it's not an easy task. And here's how I like to think of sort of why are there non-negative polynomials that are not sums of squares? Why does this happen? Should we be surprised and shocked by it, or can we sort of have an intuitive idea for why things happen? So basically the idea is that, well, let's just look at the sets where your polynomial vanishes. Okay, so I said 0 sets of polynomials. Okay, and then as the degree grows, you expect these sets to, in some way, become more and more complex. Okay, but then basically what should happen is that some 0 sets in degree twice k should not be achieved by a sum of squares, because if you write the polynomial as a sum of squares, and you look at the set of points where it vanishes, then it is intersection of the 0 sets, well, of the places where the q's, right, your squares vanish. So basically, so as the degree grows, it should happen that you have things that are more complex, and you can't realize them as intersections of 0 sets of polynomials of degree k.
This is all real.
Yeah, all real, of course. Yes. Otherwise, I can't talk about non-negative things at all. So I mean, this is just an intuitive idea. This is how I prefer to think about it, and this is just, well, in a sense, hand waving. This doesn't tell you why this should happen or anything like that. But in some sense, so this for me
This is real, but the reasoning about the zeros can be complex.
Yes, that's true. That's true. You could think yes.
Well, but then the right-hand side wouldn't be even if he is a cell.
Yes, yeah. That's right. Well, yeah, that's right. You can, well, you could think about 0 sets are a variety in complex case, but you can't reason in the same way. Okay.
But the empty set is a set of zeros of high degree complex, high degree.
Well, so the idea is that you need to come up with polynomials that have 0 sets that are so intricate or complex that you can't realize. So like the Motzkin polynomial, you could also check that it has a 0 set like that. So that, that it... I'm sorry. It's non-negative, right? So you can figure out exactly where it's 0 from. Well, because of the conditions of when AMGM inequality is the same.
Could you show us how its 0 set would be written like that?
Oh, okay. So let's look.
Oh, it cannot.
No, it cannot. That's the whole point. It's right. It's that's because it's not a sum of squares. No. You can't. But you can't. You see, if you were able to write it as a sum of squares, then you would be able to write it as an intersection.
But you can show us how it looks like.
Yes. Yeah. That's not very hard. Yeah. I mean, do you want to see it or?
There are some of us who love 0 sets. So.
Okay. Well. I mean, this is not. This is going to be quite easy because basically what happens is. All of these 4 terms, right, they have to be equal because otherwise the AMGM inequality, that's the only condition for equality. So all you get is that, I mean, it's not x squared, y squared has to be x squared, z squared. Has to be y squared, z squared. Has to be 1. So it's basically, it's all the plus minus 1s. But now you need to realize it as intersections of 0 sets of quadratic polynomials.
Well, I mean, you also need that 2 of them are negative, or I mean, the even number of them are negative. Otherwise,
Let's see, but
because you also want the negative.
For the
4x,
minus
y, z to be
4xy,
negative.
you want that to be negative because all the rest of the stuff.
oh, that's right. Okay, you're right. Yeah, that's right. Because also, yes. Yeah, okay. All right, well, I remember at one point I have convinced myself that it is true that the 0 set of the Motzkin polynomial, you can't really write it as the intersection of 0 sets of quadratic polynomials, but not sure how quickly I can reproduce it right now. So may I continue?
Yeah.
Is that okay?
Sorry, we didn't warn you to do this.
No, that's fine. It's better than you sit there quietly and then I have no idea whether you're listening or not at all. Okay. All right, so, but what I am interested in is the quantitative problem. So, all right, so there are these examples and they're hard to construct. But they don't tell us, is it true that, how do these sets compare to each other? Is our inability to construct a lot of examples, is that just because, I know there's some flaw in our intuition as to how things work? Or is it just actually, mathematically, these objects are very close to each other, so what we're trying to do is we're trying to pick objects, in two concentric sets, and then they get very, very close. So I don't know. Well, okay, I'll draw a picture later. And there is a computational motivation for this as well. If you wanted to test whether polynomial is non-negative, then it's already, so if you just fix the degree equal to 4, it's already an NP-hard problem. But testing whether it is a sum of squares, that's not, at least practically not so hard. I can't necessarily claim that it's polynomial in time, but there are practically efficient algorithms that test whether it's a sum of squares that use semi-definite programming. Okay? So that's our motive. So if the 2 sets are large, if the 2 sets are close, then we can substitute testing for sums of squares, or testing for non-negativity with testing for sums of squares. But if 2 sets are not very close, then we can't make such substitution, right? And we're still stuck with not knowing what to do about non-negativity. No. Well, you can't have too many variables, but I don't know, maybe something like 8, 9. No, for univariate polynomials, non-negative polynomials is equivalent to being a sum of squares, and testing for non-negativity should not be very hard, right? The problem is in, more variables, basically. Okay, and so what I will show is, what I will explain is that there are actually a lot more non-negative polynomials than sums of squares. And I mean, I will explain exactly what I mean by this statement as well. Okay, in what way there are a lot more non-negative polynomials than sums of squares. Okay, and I guess so I'm going to make a remark. So if a polynomial is non-negative, then we can homogenize it, right, make it homogeneous, and it will still stay non-negative. Okay, that's not hard to see, and therefore, basically, from now on, I will only talk about non-negative polynomials. Oh, sorry, homogeneous polynomials. Okay? Are there any questions right now? So now I'm sort of done with the background for non-negative polynomials, which is my motivation. So now I'm going to go into more exactly into more of what I mean by that there are significantly more non-negative polynomials than sums of squares. Oh, you can homogenize. Well, basically, okay. Let's. So if you have a polynomial, if you homogenize it, then you know that it is going to be non-negative. So let's say you add a new variable, which we will call z. Okay, so I will try to find the darker pen here. And
there's a box to your left on sitting. Just a box.
Ah, okay. Then okay, they're black. Okay. Hopefully black will be okay. And is there an eraser as well that somebody sees?
There is behind the chair.
You are right. Okay. Good. Okay, so let's say we add one more variable, which is z, right? And that's our homogenizing variable. Then, well, when z is equal to 1, we know that this polynomial is non-negative, right? Because that's what we started with. So that means that when z is also non-zero, we know that this polynomial is non-negative because it's homogeneous, right? So the only case is now, well, what happens when z is equal to 0, right? When our homogenizing variable is 0, but we have a continuous function that was non-negative everywhere besides z equals 0. So now we have it non-negative everywhere on all of, I guess now, Rn plus 1. Okay? All right, so now we turn to the case of homogeneous polynomials. Okay, so I'll ask if there are any more questions, because now I'm going to introduce some notation to explain exactly what I mean by my statements. So questions? Okay. All right, so you need to have some notation. So Pn twice k is the vector space of real homogeneous polynomials in n variables of degree twice k. And pos n twice k is a convex cone of non-negative polynomials in Pn twice k. So the set of all polynomials that are non-negative. So now, well, why is it a convex cone? So in order to check that it's convex cone, I need to check that I can basically take sums, or take, and it's pretty clear that this is a convex cone. All right, so now Sqn twice k is the convex cones of sums of squares. Okay, so it's all polynomials that are sums of squares of polynomials of degree half, so k, and also pretty clear why it's a convex cone, because I have a sum of squares, and I add a sum of squares, I still keep a sum of squares. And both of these are also, even though I didn't put it on the slide, they're closed and they're full dimensional. Okay, so they're closed cones and they have interior in Pn twice k. Okay, so now what happens is, so we have these two, well, non-compact objects, and we want to compare them in size in some way. So what we're going to do is we're going to cut them with a hyperplane. We're going to look at the compact bases that are sitting in the hyperplane, and we're going to compare those in size. Okay, so the picture is, well, not sure if I will be able to very well represent. So this is going to be sort of our, well, there are two convex cones, but this is one convex cone sort of sitting like this, and we take a hyperplane, we cut the convex cone, and in it we have the compact base. So that's the residue, and actually we have two things. So we have pos n twice k is the bigger one, and then we have sort of Sqn twice k sitting inside. Okay? So this is the mental picture that we have. Now we have two nested compact objects. Okay, so now, okay, so let me tell you what hyperplane to choose. So it's the hyperplane of all polynomials that have average 1 in the unit sphere. So the integral over the unit sphere of the polynomial with respect to the regular probability rotation invariant measure is 1. Okay?
Why is that?
Why is that a hyperplane?
No. I was going to ask why is that the way?
Oh, why is okay? Well, because you see, basically, what you would want to, if you wanted to choose a hyperplane, then you would want to choose one that is, say, is invariant under rotation. So like SON acts on the space of polynomials, and under this action, you would prefer to choose a hyperplane that would be invariant under all of these rotations. And of course, integral on the unit sphere is invariant because, well, you rotate the unit sphere, you're taking the same integral. Okay? So this is the reason for choosing this one. Well, it would give you the same. Basically, there is only. Okay, if you think about the normal to this hyperplane, then it has to be an SON invariant vector. There is only one SON invariant vector in Pn twice k. It's actually going to be important later. Well, it will be on the slide what it is, but I can write it down. It's a fairly important polynomial. It's x1 squared plus xn squared to power k. I don't know if you can see it. So basically, anything that you choose has to be perpendicular to this normal vector. And now, I mean, if you integrate with the Gaussian measure, then the integral in the sphere will be not 1, but some other constant. But basically, you will be choosing essentially the same hyperplane, right? Just moving it up or down. Does that make sense? Yeah.
Homogeneous.
Right. Homogeneous. Okay. All right. So we take the compact sections, and so now we're going to make it pos prime and sq prime are going to be the two compact sections. Okay, so basically this is our setup. We have two nested convex bodies, and now I just want to make a note as to like, well, how should we measure the size of a convex body? And well, I mean, the natural thing to say is that, well, let's take volume, right? But this will not be very good, because you would like to think is if we take volume of k, and volume, let's expand our k by 1 plus a constant. Okay, we would like to think of those two as being close to each other. Certainly, if non-negative polynomials and sums of squares were, these two convex bodies were sort of, you could expand sums of squares by a little bit and cover non-negative polynomials, certainly we would like to say that then those two convex bodies are close to each other. But what happens with volume is, well, volume of 1 plus c times k is, 1 plus c comes out to the power d, where d is the dimension. So if your dimension is very large, then being off even by a little constant is going to give you a huge factor in volume. So basically what you need to do is you need to take the volume and raise it to the power 1 over the dimension. Okay? So this is the correct way of measuring the size so that you can take dimensional effects into account.
You do not care about shape. It is not closed in the sense of one included into another.
No. Well, sums of squares are included into non-negative polynomials. But basically, I mean, well, if I show that one in volume, well, one volume raised to the power 1 over dimension is much bigger than the other, then obviously you can't expand one to cover the other because, well, volume is going to prevent it. Okay, and so just a little bit more notation. So if I'm going to talk about a metric on Pn twice k, then it's going to be with respect, it's going to be the L2 metric, so the inner product, have a Euclidean structure, the inner product of f and g is the integral of the unit sphere on the unit sphere of fg with respect to the rotation invariant probability measure. And now, so we will so B is going to be unit ball in this metric sitting in the hyperplane of things of average 1. Okay? So this is just notation that's necessary for the next slide. Or in any case, I haven't introduced a metric, so here it is. Okay, so now we go on to the sort of our main application of the orbits method. That will be the second part of this talk. Okay, so all right, so we let D be the dimension of with respect to the metric that I just introduced. I'm not saying where it's centered because all I will care about is the volume. Okay, so center it anywhere you want. Okay, but it's unit ball with respect to the previous Euclidean metric. Okay? All right, so here's the theorem. So it says, well, let D be the dimension of the hyperplane where these two convex bodies sit. then the volume of pos prime divided by volume of b, this is just a normalizing factor, raised to the power 1 over the ambient dimension, is at least some constant times 1 over square root of number of variables, then another constant 1 over square root of number of variables, and the constants depend only on the degree twice k. So, and then there are similar bounds, well, except different, of course, for sums of squares. And basically what this means is if we fix the degree and we let the number of variables grow, then as long as the degree is above, the total degree twice k is above 2, so 4, 6, these bounds are asymptotically different. Okay, and actually, so basically when the total degree is 2, right, these two sets are actually exactly the same. Non-negative polynomials are the same as sums of squares. And you can check here, so when twice k is 2, that means that k is 1, and you get exactly the same bound. Okay? I mean, they're not going to be the same because the constants are going to differ wildly in size, but at least we get approximately the same thing that, well, that's good, because otherwise we would be in trouble. Or at least I would be.
Did somebody conjecture this? Or?
Well, no. Actually, when I started working on this, when Sasha told me to look at this, the expectation was that sums of squares are about the same as non-negative polynomials. So because there is so much problems constructing the examples, and also because from the computational point of view, this is what you would want. You would want to be able to substitute testing for sums of squares, for testing for non-negativity. This way is, well, I think mathematically interesting. It's just not as applicable because it just says, well, you can't do this. So, in a sense, telling somebody that you can't do something is not as good for them as telling them that they could do something. Right? Okay.
Might save them some time.
That's true. That's true. But also, okay, so I should make some remarks. So one of the things is, though, due to the basic, so these constants depend on the degree, and some of them depend on the degree nicely, and some of them depend on the degree rather badly. I didn't want to put the exact things in. But so these bounds, they do take a while to get going. So, I mean, if you wanted to know what happens when the degree is, number of variables is like, I don't know, 8 or 10 or 11, which is, I'm not sure, but probably, if I say 20, then surely I will reach the extent of current computational possibilities. Then, well, it's not necessarily true that these two bodies have to be particularly different because the constants, I don't know, maybe you'd have to take the number of variables in hundreds in order for you to feel the difference according to these bounds. Okay? So this is a note. And, okay. So this is the theorem. So are there any questions about it? No? Okay. All right. Well, actually, we have. Okay. So now the next thing that I would like to do is I would like to explain to you how to derive the bounds. Actually, let me go to the previous slide. So the bounds that basically separate non-negative polynomials from sums of squares. So it's the lower bound here and the upper bound there. They can be derived using sort of a unified method that you can apply to other objects as well. Okay, and I will also show you sort of exactly the structure that allows us to derive these bounds. So because the non-negative polynomials, there is a lot of things happening there, but I would like to explain exactly what is going on. So now we're going to move for a while into something that is completely separate. Okay? So orbit. So we're going to have a compact group G, and it acts on a real space, real vector space V. And what we do is we take V, take a point, take its orbit under the action of the group. Okay, so the group just sort of spins it around. That's how I think about it. All right, and then we let B sub V be the convex hull of the orbit. Okay, so these are the objects that we're interested in. So convex hulls under action of a compact group, convex hulls of orbits. Oh, this is not the slide that I expect to appear. Okay, so somehow they're out of order, but anyway. Okay, So what we would like to do, we'd like to study the properties of convex bodies that are convex hulls under an action of group, and their polars as well. So what is a polar? Well, in this case, it's going to be, because basically I know all of the extreme points of my convex body are going to be the points that, the groups, the extreme points of B of V are going to be the orbit, right? Because basically I take the orbit and I take the convex hull. Okay, so in this case, the polar is going to be, well, the set of all points that the inner product is less than or equal to 1 for any point in the orbit of the group. Okay? Okay, so another way of thinking about it is that I have one linear inequality, which is basically something like x dot v is less than or equal to 1, and then this inequality, so I have a hyperplane, and this, you spin this by an action of a group, the same group, right? It's like the action on the dual space of linear functional, and this in the one hyperplane cuts out my polar. Okay, and now I'm going to give 2 examples. So one is, well, any combinatorial optimization polytope, you could think of it in such a way. Basically, the acting group is going to be ascent, so let's do the traveling salesman polytope. So here, G is going to be the symmetric group. V is the vector space of symmetric matrices, real symmetric matrices. Okay, now G acts on V by simultaneously permuting rows and columns. And, okay, slides were out of order, so let me... All right, so now we take V, the adjacency matrix of a Hamiltonian cycle. So adjacency matrix of a Hamiltonian cycle looks like... You have matrix and, well, let me pick one Hamiltonian cycle. So 1, 1, 1, 1, 1, and then also the symmetric part of diagonal. On the diagonal you have zeros and zeros everywhere else. Okay, so we pick an adjacency matrix of a Hamiltonian cycle, then we let G act on this adjacency matrix, then we take the convex hull, and we have the traveling salesman polytope. Okay, is this okay? Okay, so then another object, how does this apply to non-negative polynomials? Okay, so let's recall our compact section, pos prime n twice k is, so it's all non-negative polynomials that are average 1 on the unit sphere. Okay, well, you see the hyperplane of average 1, it's not a linear subspace, it's an affine subspace. Now I want to translate everything so everything sits in a linear subspace. So what I'm going to do is I'm going to subtract from all the points, this polynomial that is constantly 1 on the unit sphere. Okay, and what I get from, basically I'm translating everything from average 1 to average 0. Okay, and that's a linear subspace. Okay? So then so what do I get? I get pos double prime. So basically, you see, so being non-negative for a homogeneous polynomial is the same as being non-negative on the unit sphere, right, by homogeneity, right? There's no difference. So pos double prime is going to be, so once I subtracted this guy, is going to be the set of all polynomials P such that their minimum on the unit sphere is -1 and their average is 0. Okay? Are you okay with this? Right? So now let's...
Actually, don't want to subtract that thing because that thing is not
it does, because it's constantly 1 on the unit sphere.
Oh, right.
Because x1 square unit sphere is defined by this thing being equal to 1. Okay? All right, so now how does this fit into our framework? Well, basically, if we let V be the vector space of homogeneous polynomials in n variables of degree twice k, and we have average 0, our group is SON, and SON acts on the usual way. There's an inverse here to make it a group action. Basically, it acts by rotating coordinates. Then pos double prime is cut out by an orbit of 1 inequality. Right, we just pick any point on the unit sphere. Okay, so then there is a hyperplane that says this polynomial is greater than or equal to -1. Right, that's a subspace really. Okay, and then you spin it by the action of SON, and this ensures that it's greater than or equal than -1 on all of the points of the unit sphere. Okay, so this means that basically pos double prime, it is a polar of an orbit under an action of a compact group. Okay, so it has exactly the structure that I've described before.
So you're traveling fast with the group of discrete?
Yes, exactly. And here it's actually compact, right? So that's why I'm not only talking about discrete groups. Yeah.
When it's discrete, I sort of have a harder time thinking of this polar.
Well, I mean, when it's discrete, then what you get as an orbit is a discrete number of points, then you get a polytope. So then when you take the polar, you get another polytope. And actually, when it's compact, then you get some sort of a weird thing that sits in your space. Actually, it doesn't have a very high dimension, right? But when you take the convex hull, it becomes full dimensional. Okay, and then, well, when you take the polar, you get something that is basically cut out by spinning a hyperplane. Okay, are there questions? All right. Okay. Right.
So just to sort of memorize again.
Mm-hmm.
So you build the orbit by checking the action of the group and then take the convex hull.
That's right. That's right. And then you would like to study these convex bodies and their polars. Okay. All right. So our main tools are going to be studying these convex bodies by approximating them by ellipsoids, and that's something that's sort of a well-developed idea. Okay. So I'm going to talk about ellipsoids. All right. And there's basically a theorem that is due to, I guess, both John and Loevner. Well, some parts of it are due to one, and other parts are due to another. And the way that this theorem is named is exactly in the opposite way of what they did. So one of them talked about the maximal ellipsoid, one of them talked about the minimal ellipsoid, but then when people name things, they switch the names. Okay. So anyway, so it's just going to be due to both of them. So so this is a general theorem, right? And it's very useful in convex geometry. So let K be a compact d-dimensional convex body. Then there exists a unique ellipsoid of maximal volume inscribed in K, and the unique ellipsoid of minimal volume containing K. Okay, and then if we move the center of the let's say the maximum volume ellipsoid to 0, well then maximum volume ellipsoid is contained in K. But it also, you can't, if you maximize the volume, it says you cannot miss K by too much. So if you expand it by this factor, it's square root of some C that I'm going to describe times the dimension, then it's going to include your convex body. And what is C? So C is the coefficient of symmetry. So I wasn't sure that I have a whiteboard, and all I was able to do is make a rudimentary drawing on the computer. So C is the coefficient of symmetry with respect to 0. So let me now make a better drawing on the whiteboard. So here's your convex body. You take origin and you look at all the lines through the origin, and you look at the lengths that it takes. So length from 0 to 1 point on the boundaries are 1. The length from 0 to the other point on the boundaries are 2, and you maximize R1 over R2. Okay. So for example, if the convex body is centrally symmetric, then this C is always 1, the ratio is always 1, and you get the square root D. Okay? Oh, no, you minimize it. No, so the point is fixed. The point is the center of the ellipsoid. Okay? So actually, I'm not sure. So this observation might not actually be a part of the...
On the right, it should be inequality minimum.
No, it should be max, because I should be expanding by probably more than square root of the dimension.
Always choose a point such as C.
I'm sorry?
Determines the
Right. So I'm not sure that. So this observation is easy to get from the. So usually the John Loevner theorem is stated that there is D in the case of general convex body and square root D in the case of centrally symmetric convex body. But it's quite easy to get this if you look at the proof. So. Okay?
So the center for your C is the maximum or the minimum?
the center for my C is the center of the maximum volume ellipsoid. Those two ellipsoids, I mean, the similar statement is going to be true for the minimal volume ellipsoid. Of course, you're not going to expand it, you're going to contract it. Okay, and it will tell you by how much you will need to contract. But the centers of the maximum and minimum volume ellipsoids, they don't have to be the same. Yeah,
the second ingredient in this John theorem that you can find the center for which C that most square root dimension.
Well, yeah, that's also not. Yeah, that's not hard to prove. Right? Yes, that's right. That's right. Yeah, that's right. Yes. That's right. So for a convex body, right? So for general convex body, you will need to take at most D.
Yeah.
Okay.
But then you have to find the right center.
No. It's actually the center of the maximum volume ellipsoid is going to work. The coefficient of symmetry with respect to the center of the maximum volume ellipsoid, and also the minimal volume ellipsoid in case they're different, those 2 points are going to work. Okay. Yeah, that's right. Yeah, I didn't put that in, but that's not hard to prove. So that at most you will have to multiply by D. This is better than having to multiply by D all the time. Okay? Are there any other questions? Okay. All right. So well, before I go on to what's happening on the next slide, basically. So we're going to explicitly compute the minimal volume ellipsoid that contains the convex hull of an orbit, or basically by duality you can say that this is equivalent to computing the maximal volume ellipsoid that sits in the polar of the orbit. Okay? And well, so you could think, so what allows us to calculate such a thing? And I will say exactly, I mean it's on the slide, but I don't want to progress there quite yet. So why should we be able to do such a thing? Well, one of the things is that you see this ellipsoid is unique, right? The ellipsoid of maximal volume, minimal volume, they're both unique. And your convex body possesses a lot of symmetries. And the symmetries come from the action of a group. So you can definitely fix some things about your ellipsoid knowing that it possesses a lot of symmetries. Okay? And actually, in case when you have basically your action, so your representation of the group is multiplicity free, then it means that it doesn't contain copies of the same representation. Then it's pretty easy to derive this theorem, and it becomes harder in case you have copies of the same representation. But in any case, so the formulation of the theorem is actually particularly simple in case we look at the polar. So we'll look at the maximum volume ellipsoid of the polar. Okay, so what do we do? Well, basically our polar is given by inequalities x dot, inner product of x and gv is less than or equal to 1. Okay, so now what does this say? It says when is a point in the maximum volume ellipsoid? Well, when you take the square of all these inner products and you average them over the group, and when this is less than or equal to 1 over the dimension, then the point is in the maximal volume ellipsoid. Okay? So let me, perhaps on the next slide. Right, so you look basically, the polar is given by all of these inequalities. The maximum volume ellipsoid, you take the average of the square, and when it's at most 1 over the ambient dimension, and you sit inside the maximal volume ellipsoid. So this is an explicit description of the maximal volume ellipsoid, and let's apply it to pos double prime to see exactly what we get here, right? Because we have an explicit description, and we have a convex body that fits our parameters. So let's see what happens there. Oh, okay, I basically shouldn't hit that. Okay, so pos double prime is given by inequalities p of x is greater than or equal to -1 for all x on the unit sphere. Okay, so what does so what should we do? Well, we should take the square of these inequalities and integrate over the group. So basically what we get is p squared, well, we act on p by some matrix. So what happens, this rotates the sphere. Okay, so basically what it does is it computes p squared on the unit sphere, right? But it does it over all the matrices in SON. But then you can see that instead of computing the integral over SON, this simplifies to the integral over the unit sphere. Okay? So basically what you have is the integral of over the unit sphere of p squared of x. So basically what it says is that the square of the L2 norm, right, the integral of the unit sphere, is at most 1 over d. So this gives you a simple description of the maximal volume ellipsoid for the non-negative polynomials. It's basically when the L2 norm is at most 1 over square root of the ambient dimension. Okay?
So is it true that the ellipsoid you found is just the ellipsoid of the G-invariant scalar product?
Yes, but you see the representation of the SON is not trivial. Okay, so well, it's not irreducible. Mm-hmm. So there you have several components. Okay, and then in each, so basically, let's think about, so if we have a G invariant, like, so the ellipsoid by uniqueness has to be G invariant. Okay, but of course, so if you have an irreducible representation, then there is only one G invariant metric, and then basically both the maximum volume ellipsoid and the minimal volume ellipsoid, they're both bolds in this metric. The only thing is to figure out the radius. Okay, but basically, so if you have convex hull of an orbit, right, so here is, okay, so basically here's the orbit, and then we take the convex hull, then the radius is clear. It's just the radius has to be the length of the point in your orbit, right? The length of a point. And so it's easy to compute the minimal volume ellipsoid of convex hull of an orbit because it's going to be a ball, and it's also clear what to take for the radius of the ball. Okay? But now if your vector space is, if your representation is not irreducible and you have several components, and in each component you have to make a choice for basically for what happens.
Oh, it's only the radius in each component.
Right, you have to take the choice, but, okay, so this is true when your representation is multiplicity free because it decomposes in a unique way. So that's why I said the case of multiplicity free representation is fairly simple. Because if you have multiplicity free representation, then you decompose your vector space into irreducible representations, and this decomposition is unique. Okay, but if you have a representation that's not multiplicity free, then you have many different decompositions, and then you don't know exactly what to do. Okay, does this make sense?
What is multiplicity?
Multiplicity free means it does not contain the copy of the same representation. So basically, let me give an example. The idea is basically, let's say, something very simple, right? So let's say that you have, black marker, that's right. But what did I do with it? It's right here, okay. All right, so if you just take a sum of two copies of the trivial representation, so basically your group does nothing, right? Then you can decompose this sum, right? You have a two-dimensional space. You can decompose this sum into irreducible representations in any way you want, right? And this is a problem, but basically if you take, let's say, a sum of two representations, like a direct sum, W plus W. Okay, so W is a representation, and then you take a direct sum, another representation. Then, for example, the diagonal, so set of all points W comma W is also fixed by the action of G. So you have more than one decomposition. One decomposition is to say, well, let's take this copy of W and this copy of W. But another is to take the diagonal and basically the anti-diagonal, like W minus W. Okay? And this is another way of decomposing this W plus W as a sum of two irreducible representations. Okay, so when your representation is not multiplicity free, you don't have a unique decomposition. So then you don't really know, then it becomes less obvious what to do. That's all I'm saying.
Are all the examples of multiplicity free?
Well, so for non-negative polynomials, it is true that it's multiplicity free. For traveling salesman polytope, it's the representation is actually irreducible. So there, the example of the minimal volume ellipsoid for traveling salesman polytope is rather simple, right? It's just a ball.
If it's not multiplicity free,
Uh-huh.
are they all of this sort of trivial nature that you just repeat the representation?
Well, yes, yeah, of course. I mean, because multiplicity free means that you have several copies of the same representation. The only problem is that you see when I give you a thing like this, it's not clear how to decompose it, right? I can decompose it in one way, I can decompose it in another way, or in a different way. It's just, right. Okay, that's, I mean, yeah. So that just comes from representation theory of compact groups. They're exactly the same as finite groups. Okay, so this is a slide that I wasn't happy with because it contains far too many words, but in any case. Let me explain, so what can we do for the traveling salesman polytope? So let's recall that the traveling salesman polytope is convex out of the adjacency matrix of a Hamiltonian cycle. So there was an attempt to have a representative matrix of a Hamiltonian cycle. Okay, so TSP, so it sits in the vector space of all symmetric matrices, but when you take the affine span, it doesn't cut out all of the vector space. Okay, all that it cuts out is a vector space of smaller dimension, and if you basically make it from an affine space to a linear space, in the same way that we did it for non-negative polynomials, then you will find out that actually it is an Sn, it's an irreducible representation of Sn. Okay? That's not very hard to find out. So what does this mean? This means that basically the ellipsoid of the maximal volume and an ellipsoid of minimal volume, they're both balls in this metric. Okay, so computing the radius of the ellipsoid of minimal volume is easy because all you have to do is take for the radius the length of the point that you're taking the orbit of. Okay, but for the maximal volume ellipsoid, what we can do is, well, we'll have to explicitly compute the coefficient of symmetry. Okay, so that can be done. Then we know that we can scale the ellipsoid of minimal volume by this factor, and it will sit inside our convex body. Okay, and then actually we can show after this that there is a point that must be in the traveling salesman polytope and is exactly of this radius, and it's on the boundary. So this means that this is actually, so then we found the exact, the largest ball that sits inside the traveling salesman polytope. And I can't motivate this result as much as I can motivate non-negative polynomials. So the only way to motivate this is that people have tried to do this before, but were not successful. I'm not sure, because you see, when you're studying the traveling salesman polytope, what you're focusing on are its combinatorial properties, exact faces, and things like that. And I'm here interested in metric properties of my convex bodies, but it's an application of these methods. Okay. All right, so I'm almost.
Also, this John decomposition for this polytope, or
I'm sorry?
you get the John decomposition for this?
The John decomposition? I'm not sure what it means. Okay.
And there's more information inside this ellipsoid than just method.
Uh-huh. Okay, well, I'm not sure what John decomposition means, so. Okay, so yeah, so I'm almost out of time. So let me quickly describe, so how does one derive volume bounds using. Basically, the main tool is using this explicit description of the maximal volume ellipsoid sitting in the polar. Okay, so we would like to derive volume bounds. So now we need some general notation. So K is a compact convex body with origin in its interior. Okay, so the norm of K, denoted by norm sub K, is given by, well, basically it measures how much do I need to expand my convex body in order to put the point X inside it. So if you have X as a centrally symmetric convex body, then this is just like, then K becomes the unit ball of the norm. Okay, but if it's not centrally symmetric, then you don't have a norm, right? But we still call it the norm of K. All right, do you guys understand what I mean by this? Is this okay? All right. So then, well, the average norm, which is usually denoted by M sub K, and it's, I think sometimes also called the M functional. It's probably M standing for Millman. So the average norm m of k, m sub k, so this is a quantity that you use a bit if you study sort of the analytic side of convex bodies. So it's given by just the average norm x over the unit sphere. Okay. So then it's not hard to show the following binomial of volume, except it should be volume to the power 1 over the dimension. And for some reason that part has gotten lost. So the point is basically, if we want to bound volume, then it's enough to bound the average norm. That's all I want to say. And it's pretty easy to show. Okay, so what we want to do is we want to derive a bound on the average norm. Okay, so what is the norm of k when k is the polar of an orbit? Well, it should be the maximal inner product over the whole orbit, right? Because when the point is exactly on the boundary of the polar, this means that the inner product is 1. Okay, and how much I expanded by, that's okay. So this is the norm of k. Okay, so we would like to compute the average norm on the unit sphere. We would like to derive the bound for this. Okay, so let's pick a point x and define the following function. So f sub x is going to run from g to r, and the f sub x of g is going to be just the inner product of x with gv. Okay, so this is a function f from the compact group to r. Okay, and clearly norm x sub k is at most norm f sub x sub infinity. So the infinity norm is the maximum absolute value. So clearly it's above the maximum at least. Okay. All right. So now let's look at what the theorem for John's ellipsoid gives us. It says basically we can restate it as saying, so if we pick our Euclidean metric such that the ellipsoid of maximal volume is the unit ball, then let's look at the L2 norm of f. So this is norm f of sub x of sub 2. So it's the integral of the square to the power 1/2, right? So when we integrate the square, we get integral of x dot gv squared. Okay, and since we're on the boundary of the maximal volume ellipsoid, okay, then we're going to get 1 over d. So here we want to pick x in the unit sphere, right? Because we're going to bound the average of this over the unit sphere. So if x lies in the unit sphere, and we picked our metric such that the ellipsoid of maximal volume is the unit ball, okay, so then when x is on the unit sphere, it says that when we integrate the square, take the square root, there should be 1 over square root of the dimension. Okay, so this is, let me maybe...
It's not the unit ball, it's the 1 over 3 ball.
Oh, I see. Okay. You're right. No, actually it is. So that's okay. So here's the, okay, so if we make this, so then, okay, so it says that basically the ellipsoid of maximal volume is given by the following equation. So when we integrate the square of x dot gv, we get 1 over d. Okay? So then when we pick a point on the boundary, then when we integrate the square and take the square root, it should be 1 over root d. Okay? Okay, so basically what happens is that this, the maximal volume ellipsoid tells us something about the L2 norm of f sub x. But what we would like to do is we would like to get a handle on the L infinity norm of f sub x. So how do we do this? Well, the plan is to estimate the L infinity norm by high L twice k norms, right? So by high LP norms. Okay, so that's a standard thing, and we can do it because we have a function from a compact set, right? Because we have a compact group. Okay. All right, so how do we do this? Well, basically the idea is we're going to consider not the orbit of V, but the orbit of V tensor, some high tensor. Okay, so we can take our representation, we can take a tensor power of it. Okay? So then what happens is then, okay, so you can derive a bound, so using this you can derive a bound on the L infinity norm using the L twice k norm, and once we take a sufficient power of sufficiently high k, and we put all the pieces together, we get the volume bound. So I think that's enough time. Okay, so all right, so okay. In an attempt to finish on time, I skipped something that was on top that is crucial. Okay, so it's on this slide, so I can explain it rather quickly. Okay, so basically what happens is, okay, let me go. Okay, so you know that the L2 norm on the boundary of the unit ball, on the boundary of the maximal ellipsoid is exactly 1 over square root of d. Okay, then if you expand it d times, then it's going to contain your convex body. Okay, and on the convex body, the L infinity norm, well, the maximum is 1, but if you take the minus the convex body, then you will get that the L infinity norm is 1. So then what should happen, what you get is, so since k is contained in d times E max, and minus k is also contained in d times E max because, well, the ellipsoids are centrally symmetric. Okay, it happens that the norm f sub infinity is at most square root of d times norm f sub 2. Okay, because it used to be that norm f sub 2 on the ellipsoid was 1 over square root d, and now you multiply the ellipsoid d times, so that's why you get square root of d. And d is the ambient dimension. So now I can explain better what happens here. So here you take the tensor power, but you see your point v tensor twice k, it can only span out as much as the symmetric part of this representation. So you can only get symmetric tensors when you look at the affine span of v tensor twice k. Yeah. Yeah, that's right. Oh, yeah, right. So this should say the dimension of this, right? So this is why. Okay. So this is why there is a. This is why you can gain, because instead of looking at the whole dimension of the tensor power, which is not going to gain you anything, you only need to look at the dimension of a high symmetric power. Okay, and then therefore you get this inequality. Okay, there should be dimension there. That's right. And then this allows you to take k high enough to estimate the L infinity norm, and then you actually need to look. You need to look at the actual representation, because so what happens with right? Well, because there are further things that you can win if you look at a particular example, because your v tensor twice k doesn't have to span the whole symmetric power either. Okay, so if it happens that it spans even less, then you get a better bound, and you need to take a smaller k. Okay, and then, well, basically all the pieces need to be put together, and you get the volume bound. And yes, that was the last slide.
Who's next on your schedule? This is your schedule.